adjoint of a matrix. So adjoint of a matrix, how is it defined? It is like if A is matrix A1 B1 C1, A2 B2 C2, A3 B3 C3. Okay, then cofactor of A is you replace the elements by their corresponding cofactors. And then take a transpose. So adjoint of A is take the transpose of the cofactor matrix of A. That is what is adjoint. A1 B1 C1, A2 B2 C2, A3 B3 C3. Okay, so this is transpose of the cofactor matrix, that is the adjoint of a matrix. Now this adjoint has a number of properties. First property, let us examine. Very important property. Based on this, we define the inverse. What is A into adjoint of A? A into adjoint of A. Let us see. A1 B1 C1, A2 B2 C2, A3 B3 C3 multiplied by A2 A3 B1 B2 B3 C1 C2 C3. So you see A1 capital A1, B1 capital B1, C1 capital C1. So your first element will be nothing but determinant of A. Okay. The second element A1 A2 plus B1 B2 plus C1 C2. Elements of the first row multiplied by the cofactors of the second row. We get 0. Just now we showed elements of one row multiplied by the cofactors of another row. We get 0. So that's what we have got here. Next, elements of the first row multiplied by the third column. So this is the cofactors of the third row. This will again be 0. Let us look at the second row elements now in the product. Second row multiplied by the first column. A2 A1, B2 B1, C2 C1. It is second row elements multiplied by the cofactors of the first row. We get 0. Yeah. Then second row multiplied by the cofactors of the second row, we get determinant. Second row multiplied by the cofactors of the third row, you get 0. Similarly for the last, the third row multiplied by the cofactors of the first row, A1 B1 C1, and when you add, you get 0, 0 and determinant of A. So this becomes determinant A multiplied by 1 0 0 0 1 0 0 0 1. Okay, so this becomes determinant of A into I. This is a very important result. So we can show the other way also. We showed A into adjoint A. We can show also adjoint A times A. Both will yield to determinant of A into I. Determinant of A into I. Okay. So this is the one of the fundamental properties of adjoint of a matrix, and there are other properties. This forms the most fundamental property. Okay, so these are the properties of the adjoint matrix. So the first one I just now highlighted, A into adjoint A is adjoint A into A, which is determinant of A into I. Now In, because n is the order of the square matrix of A. Now second property, if A is the square matrix of order A, of order n, okay, then adjoint of A transpose, the dash that we are writing is transpose. So here adjoint of A transpose is same as adjoint A the whole transpose. And next property we have adjoint of AB is same as adjoint B into adjoint A, just like AB whole transpose is B transpose A transpose. Now these are some additional properties, you little advanced level we don't need right now for at our level of problem solving in GATE. However, you can look into it. Adjoint of adjoint A, how do you find? Is, I'll just show this. See, okay, now we had A into adjoint A is equal to determinant of A times In. Now let us replace A by adjoint A. So adjoint A times adjoint of adjoint A. So I'm replacing A by adjoint A. What do I get? I get adjoint determinant of adjoint A by In. How do you get this? Obtained by replacing A with adjoint A. Okay. So now what do you get? Now I want, my target is to find A into adjoint A. So what I do, I'll simplify the right hand side first. Now I'll go back to this equation 1 and I will do this. I will take determinant on both sides. Determinant of A into adjoint A is determinant A into In. Determinant of A into In is nothing but determinant of this scalar. sorry, determinant of this diagonal matrix, which is determinant A to the power n times determinant of I, and determinant of I will always be 1. Okay. So, and we know determinant of AB by the property is determinant A into determinant B. So from here we get determinant of adjoint A is determinant of A to the power of n minus 1. Okay. So now, so I want to find adjoint of adjoint A. So what did I find first? Determinant of adjoint A I found. So this equation 2 now we can write like this. Adjoint A times adjoint of adjoint A is equal to determinant of adjoint A times In. So determinant of adjoint A is determinant A to the power n minus 1 times In. I want this matrix, what it is. I'll multiply with A throughout. So by associative law, A times BC is same as AB times C. So I can write A into adjoint A times adjoint of adjoint A. This determinant is a number, it's a scalar, and I get A times I. Okay, this is just a scalar, so I can take it out. Now A into adjoint A is determinant of, go back to the basic, determinant of A times In A into I is A. This is a scalar now, and this product, identity matrix multiplied by any matrix, is the matrix itself. So adjoint of adjoint A, and this is a scalar, it is not a matrix, it can be pulled down here. I get determinant of A to the power n minus 2 times A. Now you can do the determinant of this. So this property I've shown, and this property just extension of this. You can just work it out. So this is adjoint. Now we come to inverse of a matrix. So inverse of a square matrix. How is inverse defined? So how do we get inverse? So okay, if A is a non-singular, is a matrix such that determinant of A is not equal to 0, that means it is non-singular matrix. Singular matrix means a matrix whose determinant is 0. Now if A is a matrix such that its determinant is not 0, then there exists Matrix B of the same order as A, such that AB is equal to BA is equal to I. I is the identity matrix. Okay, so now let us look at this now. What is this B then? Then B is called inverse of A and is denoted by A inverse. Okay, so basically we want A into A inverse is equal to A inverse into A is equal to I. We want to find what is this matrix A inverse. Let us go to adjoint. This property, this particular property, A into adjoint A, we just now built that. So A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into I. Because A is the scalar, I divide determinant A is a scalar, I divide throughout by determinant A. Now what I do, I take determinant inside this scalar. I can multiply it either with the first one or the second one. I choose to multiply with the second. Here I get adjoint A upon A. Now you compare. AB into BA is equal to IN. AB equal to BA is equal to IN here. So this means this particular matrix is the inverse. All right. Therefore, A inverse is adjoint A by determinant of A. A inverse is adjoint A by determinant of A. So this is how we get the inverse, and we have properties associated with inverse. Of course, some basic properties. I'll not enlist all. This you can review. If A and B are two matrices, then AB whole inverse is B inverse A inverse. If there are three matrices, then you have C inverse, B inverse, A inverse. Okay, so on. So are you following so far? All right. Now I'll soon give questions for solving. We will solve these questions now based on these. Now these are some basic properties. One more important property is A transpose inverse is same as A inverse transpose. These are commutative. Uh, these are commutative, and very important. cancellation laws, how do it work? AB, if AB is equal to AC, then B equal to C if determinant of A is not equal to 0. Because how you get this? We multiply both sides by A inverse. Then this A inverse times A becomes I, and I times B is B, I times C is C. Okay, so we have to multiply by the left. Multiply A inverse on the left. If the common matrix is on the right, we have to multiply the inverse from the right. So these are some properties.